In the previous lecture, we talked about qualitative characterization of the partially folded states of protein. We discussed the use of circular dichroism spectroscopy, which can qualitatively establish the relative change in the secondary structure and tertiary structure of a protein compared to the native state. By taking the example of hexafluoroisopropanol with alpha-lactalbumin, what we observed was that at certain concentration of hexafluoroisopropanol, the CD signals suggest that the secondary structure is rather strengthened compared to the native structure, but the tertiary structure is lost. And therefore, these features suggest that the protein under these conditions is in the molten globule state. There are other qualitative methods which can be applied in the studies of the molten globule state or partially folded states. A look at literature suggests that fluorescence spectroscopy has been extensively used also in the characterization of the partially folded states of protein. Fluorescence spectroscopy details is a matter of a different lecture. However, the fluorescence spectroscopy of proteins has given tremendous information not only about the conformational changes in proteins, but also about the protein ligand binding. Several proteins have tryptophans, and therefore, the fluorescence due to the tryptophan, that is selectively exciting at 293 nanometer or a suitable wavelength and looking at the emission spectra, gives information about the conformational changes and even the protein ligand binding. Therefore, the changes in the fluorescence emission intensity and the changes in the fluorescence emission wavelength where the maxima appears gives lot of information, as we will discuss a bit later how it gives. Now let us take a look at the slide. This molecule 8-anilino-1-naphthalene sulfonic acid has been extensively used in literature in the characterization of the partially folded states. How and why? If we look at the molecular structure of ANS, it has a good hydrophobic component and it also has a sulfonate group. So therefore, this molecule can bind to hydrophobic clusters through hydrophobic interaction over here, and also it has ability to undergo ionic interaction. And therefore, this dye or this molecule has been extensively used in the characterization of the partially folded states. When the protein is in an in-between state, that is the partially folded states such as the molten globule state, where it is not completely unfolded. So therefore, the Mg state will have several hydrophobic clusters available, and the molecules like A and S can go and bind to those hydrophobic clusters. and hence this will lead to change in the fluorescence properties of the ANS. And that is why ANS has been extensively used in the characterization of the partially folded states of proteins. Let us take a look at the comments. ANS fluoresces under non-polar conditions with the increased intensity because of the interaction of the non-polar moiety with the non-polar acceptors. That is why the partially folded states can be identified by fluorescence using ANS. What happens is, when ANS binds to the partially folded states or non-polar clusters, the emission intensity goes way high, becomes way high. The fluorescence emission intensity of ANS, for example, in this particular case, where the concentration of the additive is 0, is here, and 0.5 molar of hexafluoroisopropanol induces molten globule state in protein. So, this emission corresponds to those conditions where 0.5 molar hexafluoroisopropanol has been added to alpha lactalbumin, and since the protein under these conditions is in the molten globule state, you see the fluorescence emission of ANS is very high compared to other concentrations of hexafluoroisopropanol where the protein is not in the molten globule state. Either it is native, 0 means 0 hexafluoroisopropanol means the protein is in the native state, here 0.5 molar molten globule state, and above that it is pushing the protein into denatured state. And that is why the comments, if we re-look at the comments, ANS fluoresces under non-polar conditions with increased intensity and partially folded states can be identified by fluorescence. So, not only that, the ANS energy transfer, because if the emission intensity or the wavelength at which the emission is observed overlaps with the absorbance, the energy transfer from some amino acid residues to ANS, if there is an overlap between the emission wavelength and the absorbance wavelength, the energy transfer can give information also about the conformation of a protein. For example, the wavelength at which the tryptophan emits coincides with the wavelength at which ANS absorbs, so therefore energy transfer is possible. And since the unfolding of protein also changes the environment of tryptophan, that is why the energy transfer can also be used to correlate the changes with the conformational changes in the protein. The comment that I want to make over here based upon these fluorescence observations is that the ANS fluorescence has been used for a long time in the characterization of partially folded states of proteins. But such characterization is also qualitative in nature. In order to make the characterization quantitative, quantitative means we should be able to assign the thermodynamic parameters. Let us see some more examples. Now we will start discussing how the thermodynamics of the process can give information about the molten globule state. Let us take a look at a typical differential scanning calorimetric output. In a DSC, what we have is Cp versus the temperature, and we have a differential scanning calorimetric profile from which we get delta H calorimetry and delta H Van 't Hoff. These two are obtained. Right. Delta H calorimetry comes from the area under the curve and delta Van 't Hoff comes from the shape of the transition. Now, this ratio of Van 't Hoff enthalpy to calorimetric enthalpy gives information about the mechanism of the folding unfolding process. Suppose if this is equal to 1, we have earlier discussed that if Van 't Hoff enthalpy is equal to calorimetric enthalpy, then the unfolding process is two-state. Two-state means either native state is significantly populated or denatured state is significantly populated. If Van 't Hoff enthalpy over calorimetric enthalpy is less than 1, that means there are intermediates. In the unfolding process, then the mechanism is no more n going to d, then there could be, for example, n is in equilibrium with I, intermediate is in equilibrium with d. It suggests if the Van 't Hoff enthalpy is less than the calorimetric enthalpy, the conclusion to be drawn is that there are one or more intermediates appearing in the overall unfolding process. The third possibility is Van 't Hoff enthalpy over calorimetric enthalpy is greater than 1, and that suggests intermolecular cooperation. Intermolecular cooperation in the unfolding process. What is this intermolecular cooperation? Intermolecular cooperation is that when the protein is unfolding, then the two unfolded proteins can sort of form a dimer, trimer, oligomer, aggregate. So, extent of aggregation will increase. So, therefore, this comparison of calorimetric and Van 't Hoff enthalpy can be used to establish whether the folding unfolding process is two-state, or it involves the formation of an intermediate state, or the unfolding is involving intermolecular cooperation. Let us take some examples from literature to discuss this in details. This figure, which is adopted from biochemistry, is a plot of excess heat capacity against temperature, or in other words, it is a DSC thermogram for unfolding of apo-alpha lactalbumin at increasing guanidinium hydrochloride concentration. Apo-alpha lactalbumin. What is apo-alpha lactalbumin? Apo means you have removed the cofactor, you have removed calcium from it. So, once you remove calcium from alpha lactalbumin, obviously it will lose its stability. and it should go into an intermediate conformation in between native state and denatured state. Let us take a look at the figure. When the concentration of guanidinium hydrochloride is increased in solution, please take a look at how the area under the curve decreases, and even there is a left hand side shift towards the transition temperature. This is cold denaturation, so let us not focus on this at present. Let us focus on heat denaturation. What they observed, that when you increase the concentration of guanidinium hydrochloride, the calorimetric enthalpy decreases as well as the transition temperature decreases. They also studied the thermal unfolding of lysozyme along with alpha lactalbumin and made some general conclusions. What they observed, that the calorimetric and Van 't Hoff enthalpies for apo-alpha lactalbumin in presence of various concentrations of guanidinium hydrochloride are not equal, whereas the calorimetric enthalpies and Van 't Hoff enthalpy for thermal unfolding of hen egg white lysozyme are equal. I repeat, what they observed is that the calorimetric enthalpy and Van 't Hoff enthalpy for the unfolding of apo-alpha lactalbumin in presence of guanidinium chloride are not same, whereas these two enthalpies are same when it comes to hen egg white lysozyme. And the ratio of Van 't Hoff to calorimetric enthalpy suggested the formation of an intermediate state. So based upon this non-equivalence, you see the calorimetric enthalpy varies like this, Van 't Hoff enthalpies varies like this, there is non-equivalence, and the non-equivalence, they use this information to suggest that guanidinium hydrochloride induces the molten globule state of a protein. However, let us keep in mind that these authors suggested that the molten globule state of a protein shows a cooperative thermal transition which is smaller than the one obtained with the native state. As we keep on increasing guanidinium hydrochloride concentration, the height of the peak is decreasing, that means area under the peak will keep on decreasing, as well as there is a shift towards the left side. Similarly, molten globule state of cytochrome C has also shown cooperative thermal transitions in the differential scanning calorimetry. As I mentioned in one of the lectures, that when you lower the pH of a protein, for example in the case of cytochrome C, if you lower the pH to 1.8, that corresponds to zero line. Zero line means there is 0 molar additive in that. There is no thermal transition observed. However, when you add 20 millimolar sodium perchlorate, we get a well-defined thermal transition. When you increase the concentration of NaClO4 to 50 millimolar, the thermal transition temperature further increases. That means NaClO4 is inducing renaturation or it is inducing structure in the unfolded protein, and these authors termed these states as molten globule states. And they also performed isothermal titration calorimetry on the interaction of NaClO4 with cytochrome C and gave the information on enthalpies of interaction. As you can see, in a specific manner, NaClO4 is interacting with cytochrome C. And these kind of experiments can give the enthalpies of interaction along with some other thermodynamic parameters. We will discuss about these bit later, but let us for the time being concentrate on differential scanning calorimetry. What I have discussed is that some authors have shown that the molten globule like state show a differential scanning calorimetric profile, well defined differential scanning calorimetric profile, the height of which or the transition temperature is less than that compared to the native state. But there are some other controversial reports also available in literature. Let us discuss about those. Immediately after those reports, another report appeared in literature where they performed differential scanning calorimetry of apo-alpha-lactalbumin and holo-alpha-lactalbumin. And let us discuss what they observed. Let's take a look at this figure. This figure shows the DSC of holo-alpha-lactalbumin. This well-defined thermal transition corresponds to holo-alpha-lactalbumin, and the flat line represents the DSC profile of apo-alpha-lactalbumin. What these authors showed that the DSC of apo-alpha-lactalbumin did not show an endotherm. And simultaneously, if you look at the CD of apo-alpha-lactalbumin, if you look at the secondary structure and tertiary structure, the far UVCD and near UVCD, the secondary structure of apo-alpha-lactalbumin is almost similar to the secondary structure of the holo-alpha-lactalbumin, whereas the tertiary structure of apo-alpha-lactalbumin is almost lost, whereas it is intact for the holo-alpha-lactalbumin. That is why the comment is made, tertiary structure is lost but secondary structure is intact. So here comes the controversy, because in this example the authors showed that the molten globule state, the traditional molten globule state for which the definition adopted is intact secondary structure compared to that of the native state and lost tertiary structure. It did not show an endotherm in the differential scanning calorimetric profile. Now let us discuss that what leads to the formation, what leads to an endotherm in the differential scanning calorimetric profile. The folded form of a protein or the native structure is stabilized by secondary structure interactions and the interactions which are responsible for holding the tertiary conformation intact. Secondary structure largely has hydrogen bonding, and after that in the tertiary fold, in addition to hydrogen bonding, you have hydrophobic interactions and some other ionic interactions. Now out of these two, which one is a cooperative process? The endotherm which is observed in the differential scanning calorimetric output profile is a cooperative transition, and that cooperative transition is observed when the tertiary structure is lost. What is meaning of a cooperative process? A cooperative process is the one in which one step facilitates the formation of the next step. In other words, if one bond is broken, it facilitates the breakage of the next bond, and vice versa. So when a protein is heated, when it starts unfolding, the unfolding cooperative process is due to the loss of the interactions which hold the tertiary structure of the protein intact. And if in a protein the tertiary structure is completely lost, therefore it is not expected to show a cooperative thermal transition. And based on these arguments, these authors, let's look at the figure, these authors claim that the apo-alpha-lactalbumin, in which the tertiary structure you see is lost, look at in the CD spectra, secondary structure is intact, it is not expected to show a cooperative thermal transition. Whereas the holo-alpha-lactalbumin, which has intact tertiary structure, should show the cooperative thermal transition. And after this report, several other papers appeared in literature which showed that the molten globule state in several proteins does not show a cooperative thermal transition in differential scanning calorimetric profile. So therefore, if we do not see an endotherm in the differential scanning calorimetric profile, that means if it is just a flat, is a straight line, then we should not conclude that the protein is already denatured, because the protein may be in some intermediate form. Let us take a look at the figure again. If we get a flat line like this, then immediate conclusion should not be drawn that the protein is in the denatured form. As demonstrated over here, there is no thermal transition observed here, but still the protein has secondary structure which is almost same as that of the native state, but has poorly defined or lost tertiary structure. So therefore, absence of a cooperative thermal transition in DSC should also be interpreted as that it could be, the protein could be in an intermediate structure, and it should be verified simultaneously by the application of spectroscopic methods. And one such spectroscopic method which gives direct information on the secondary and tertiary structure of the proteins, as we just discussed earlier, is circular dichroism spectroscopy. So what we discussed in this lecture is that fluorescence and circular dichroism spectroscopy, and I am sure some other spectroscopy, can also give information about the formation of partially folded states of the protein, but most of the information which is available based on the spectroscopic methods is qualitative in nature. Now we have started discussing the quantitative aspects. First we discussed that the literature shows that the molten globule state shows a cooperative transition, but some authors showed that the molten globule state, which fit into the definition of no tertiary structure but intact secondary structure, it does not show a cooperative transition. So therefore we can interpret these controversy in the sense that a state in which the secondary structure is still intact or more than the native state, but the tertiary structure is lost, is not expected to show a cooperative thermal transition. We still have to discuss that how to get more quantitative information about these partially folded states, and those quantitative thermodynamic informations give what kind of information about the common structural features or the structural features of these partially folded states. We will discuss these matters in some more details in the next lecture. Thank you very much.